Hello, fellows. We're going to be solving this question paper. Um, and there are going to be 4 questions in paper 4, alternative to practical. And you must remember the fact that question number 1 is going to be related to a graph where you're going to compare two values, one against the other with other control variables. And you're going to obtain 5 to 6 values and you're going to plot a graph. The independent is going to be on the x-axis and the dependent value is going to be on the y-axis. And one of the simplest approaches to take and to answering these questions is to read the question carefully, and if you do that, break it down, and then it's going to be very simple in the fact that all you have to do is address the question asked without any inhibitions, without feeling any doubts. Like, for instance, let's have a look at this question. A student determines the speed of waterfront and on the surface of water. The student fills a plate with water and uses a dropping pipette to let one drop of the water fall into the center of the plate as shown in figure 1.1. So basically what he's doing is he's emulating a ripple tank on a very it's something that he could carry it out in the classroom or at home even. All right, so you fill the water up and then going to be ripples that are going to move across in a circular way. So the wavefront that is produced travels outwards to the rim of the plate and then reflects back. So this is going to be important, reflects back to the center. Okay, it goes like, now figure 1.2 shows a scale marked on the side of the dropping pipette. Now these are the scales. All right, so 0.5, 1, 1.5 and 2 centimeter cube. Describe the technique the student uses to put 1 centimeter cube of water into the dropping plate. Now, this seems something very confusing for a student, might seem confusing because of the fact that, oh, what this is like, what does he want us to do, scientifically speaking? But the question is quite straightforward. Describe the technique the student uses to put 1 centimeter. How is he going to get 1 centimeter cube of water into the pipette? Now, and there are 3 marks for that. So mind you, there have to be 3 points. So your first point has to be, you have to squeeze the bulb. All right. Why would you do that? To let the air out. All right. Dip the second part is going to be dip the open end of the pipette into water so as to suck up the water. This would be the third point, to suck up the water. No, this is not the third point. Sorry, to suck up the water. Now, he says 1 centimeter cube. All right. So your third point has to be squeeze out excess water until it is in line with 1.0 centimeter cube. That's it. Those are the 3 points. Now, what I'm trying to tell you over here is that when you're thinking about the technique, there are 3 steps. You squeeze the air out, put it into water, or you could even do it while it's in the water. Squeeze the air out, let it suck up the water. You have to say that, and then squeeze out the excess water to make it 1 centimeter. That's the technique that we're going to use. Okay, there's no, I mean, we could take a syringe and put 1 centimeter cube of water, but that's too complicated. I mean, if you said that, we don't really have a syringe. It doesn't say we have a syringe right now. Okay, so that's one of the ways of doing it. The student observes the wavefront travels outwards from the center of the plate and then reflects back from the rim back to the center. Is a side view of the wavefront as it spreads out across the diameter d of the plate. The student uses a stopwatch to measure the time taken for the wavefront to travel. Now, outwards from the center of the plate and then back to the center. It shows 3 readings for time t. Use the stopwatch readings, figure 1.4, to determine the accurate value for t. Now, must remember that there are 3 values given, so you just write 1.12 plus 1.17 plus 1.02, and then you're going to divide all this by 3. What are you going to get out of this? Now, here you go. If I did that, 1.12, which is this, 1.17 plus 1.02, you get 1.10333. So if here's what 1.10. Now let's say if somebody said and wrote something like 1.103 and another one wrote 1.1. Now mind you, there are three significant figures, so make sure you have three. All right, this would be maybe perhaps the mark scheme allows this, or it may not. All right, so be careful with that. It's best to stay with the number of significant figures, because if in a year they're not going to accept these answers, or they might in the mark scheme. So if you wrote this, you're at a risk, but if you wrote this, you're at risk, but if you wrote that, you're surely in the safe zone. The speed of the water flow can be calculated using the equation distance over time, like duh. So this is your distance, and the time you already have. This is your time, 1 seconds, okay? Seconds is written over there, so even if you forgot to write, it wouldn't matter. Now, it's drawn to scale. It's half the size of the plate. So the scale is 1 to 2, all right? That means we'll have to multiply it by 2 to get the real, because it's not the real size of the plate. Now, used in the experiment. Calculate the speed of the wavefront using the answers from B1 and the measurements taken from 1. Okay, let's take the measurements now. So if I bring a ruler, this gives me about 11.4. Okay, so I'm getting 11.4 with this ruler. Let me check it out with this ruler, and it's exactly the same. It is 11.4, as you can see, 11.4 there. So 11.4, all right. And now we have to multiply that by 2, because this was half the size. So that'll be 22.8. This is the length, the actual length, the distance is going to be traveled. So speed is going to be, the speed is going to be 22.8 divided by 1.10, which is divided by 1.1, and that's 20.73. So I'm just going to write the speed is 20.7 centimeters per second. But luckily for you, the units are written. Okay, let's go to the next part. So here we have C part. Then this is something that I don't know why students get scared with. Identify 2 causes of uncertainty in this experiment. Uncertainty, that means how would this impact the result that you're having. That means in measuring the 2 in this experiment. So since we're measuring distance and time, so that means measuring this distance d and this time. So if we look at that. Now, if you think about this, this is the situation, and in reality, when you try to put the ruler on top of that, you know, it's going to be difficult. One, to make sure that the drop actually hits exactly at the center. What if you're dropping it here or dropping it over there? So the drop may not be exactly at the center, making it it will be difficult to make the drop right at the center. It'll be difficult to keep the ruler right above it, because otherwise it'll touch the water and create ripples. So holding the ruler steadily above the plate to measure this, the waves are going to move too fast for you to start and stop the stopwatch. What else can we think about? The reaction time, because there's time involved, the reaction time of the person in avoiding the parallax error while keeping starting and stopping the stopwatch. All right, what was the next part? So should I repeat that? Yeah, you could actually rewind, and since it's going to be a video, you could always go back instead of me having to repeat that. Suggest 1 improvement that could be made to this experiment. There you go. That's going to be simple. Like for instance, if you were, this thing is bleeding, so let me get one of those ballpoint pens. Here you go. So if we had this plate over here, right, and I were to mark with a permanent ink the center and then fill it with water, it would be easier for me to drop it on the dot. Okay, so to mark the center of the plate, the ruler, if it could be clamped right above the right like that, so that the ruler doesn't move. It could be clamped over this. We could use a larger plate, which makes things easier as well. Okay, so those could be, it just says one, but we have looked at a few more. Let's get to the next question. Now, a student investigates the resistance of a resistance wire. Okay, so the crocodile clip. Now, one of the things when you're taking this, I would like you to take the time out to study the diagram. So there's a battery, there's a switch which is off, and the current goes through this resistor, and then we measure the voltage across this 10 ohm resistor, which is a known resistance, and then there's the unknown resistance, because there is a variable. The greater the length of the crocodile clip between this point and the crocodile clip, the greater the resistance. Over here it will be the minimum resistance, over here is the maximum resistance, and so on and so forth. So the crocodile clip attached to the flying lead is connected to different points along the length of the resistance wire. Okay, shows the voltmeter when the flying lead is connected to the resistance wire at the 100 centimeter mark over here on the ruler, and switch is closed. So that is kind of like maximum resistance. Now, if you realize this, if it was over here, right, what's going to happen is the voltage that we'll get over here would be a smaller voltage, because most of the voltage is across this now. And if it were here, we would probably get the full voltage of the power supply over here, because there's no resistance. So the entire resistance is over there. So this voltage would represent the actual voltage of the motor. But when it's over here, it gives you a maximum voltage across this, so minimum voltage over there. So that will be the smallest. But anyway, he's not asking us that. Read the voltage shown on figure 2.2 and record the reading on table 2.1 on page 6. What you're going to do is, we know this is 0 and 1, right? So that means if you divide 1 over 10, because there are 10 divisions between that, right? So we get 0.1. That means every single small division over here, every single small division from here to here is 0.1. So, but this one over here is very clearly between 1.567 and 8. So it's between 1.7 and 1.8. Now, when he asks you to take a reading, and the value is between these two, don't write 1.74 or 1.76. Don't write anything like that. Between these two, it's going to be 0.5. Okay, so your reading over here is going to be 1.75 volts. Okay, so make sure it's, because I have told you the least count over 2 is the estimated value. Whatever your least count is, because this is the least count, is 0.1. So 0.1 over 2 is going to be 0.5. So you cannot, any smaller value than 0.5, you cannot estimate anything smaller than that. Okay, so the value which has to be guessed can be the half of the least count. Okay, now he's probably going to ask us to write that down on a table. All right, calculate the current I for each length L shown in table 2.1 using the equation this. Record your answer in table 2.1. So answer, this is going to be 1.75, which is right, because there are all three significant figures here. So we write that down. Now, V over 10. Why is I is equals to V over 10? Because I is equals to V over R. So that means the resistance was R was 10. Yeah, our resistance is 10 ohms. Note that it's 10 ohms there. So whatever your voltage you're measuring across that voltage divided by 10 would give you the current. So the current is going to be, so we're going to fill this up. We get 1.75 divided by 10. Obviously, it's going to be 0.175. So let's stick to 3 decimal places. 2 divided by 10 is, so I'm going to write 0.2. Don't just write, do write 00. Okay, so this is going to be 0.230. That's going to be 0.270, and this is going to be 0.320. All right, and then you have to take a reciprocal of these values, which is going to be 1 divided by 0.175, which is 5.71. 5.71, and let me fill it up now. Now, since all these third ones are kind of redundant, if I wrote this as 0.18, okay, over here, then ignore these. So there are 2 decimals. 0.18 1 divided by 0.18, I get 5.55, no, let's stick to this, 1.75, which is 1 divided by 0.175, and that's 5.71. Okay, so here do we have it: 5.71, 5.00, 4.34, 3.70, 3.12. Now, record your answers in table 2.1. Calculate the values one for each length shown. Record your answers in figure 2.1. Write the units on top of the row. This is something very important. You keep forgetting this. So length was given in what, right? You could put a bracket over there and write in centimeters. Voltage was given in volts. Current was given in amperes. And 1 over amp should be 1 over amperes. Okay, so that's the way it's going to be. These are your units. Okay, once we're done with that, draw a straight line of the best fit. Extend this line to intercept the y-axis. Determine the gradient of y-intercept of this line. Show clearly the graph, the values you choose, and show your working. Okay, now on this is what I'm going to do over here. I'm going to keep this as well. Just if I could take this off just for you guys. Now on the grid on page 7, this is page 7 over here. Okay, so how do you choose your values? Let me tell you about that. Now here comes a part that is, I think, the most complicated, because you take it very easy. Some of you are very good at drawing a scale, but I'm going to teach you a method that should not leave any doubt to errors. What I'd like us to do is that understand. First, count how many like I have a scale of 10 small squares, 10. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got 12 large squares on the y-axis, and 1, 2, 3, 4, 5, 6, 7, 8 large squares on the x-axis. So let's have a look at the y-axis first. On the grid on page 7, plot a graph of this. That means we have to plot a graph of this on the y-axis. This is the y-axis. And L on the x-axis, which is this on the x-axis. So leaves no doubt. So if you're going to mess this up now, you're going to lose those marks. And not only lose those marks, you're also going to lose your credibility not following the instructions. So please don't make mistakes on this. But the thing is, let's have a look. Start both the x's at the origin. Now that means this has to start from 0 onwards. So let's see how you choose your scale. So here, in order to choose your scale over here, let me give you an idea. I needed a blank paper here, but so let me just put for this one, for the scale, what we're going to do is that 5.71, divide by 12, because there are 12 large squares over here. So let's see what we get for that. 5.71 divided by 12 gives you whatever the value, 0.475. And this would be, if we use this 0.475, that is 0.475, and then increment in 0.475, we'll get to 5.71 over here. But that's not going to be a easy scale to read. And if I were to use this scale, 0.951, then I would be able to get half the graph. So clearly I can choose a value between that. So I can see 0.5 is a very good number over here. Okay, between 0.95 and 0.475, 0.5 is a nice round number. So if I did this with, like, this is 0, 0.5, 1.0, 1.5, 2.0, 2.5, 3.0, 3.5, 4.0, 4.5, 5.0, 5.5, and 6.0, which easily comes to the highest number, 5.71. So we're getting a very good scale over here. Let's try the same thing for this. And for this, we see the scale has to go from 0 to 100. So that means 100 is the total. And there are 8 large squares on this side, 8 large squares. So 100 divided by 8 gives you 100 divided by 8 gives you 12.5. Sorry, 12.5. Multiply that. That would be, if I use 12.5, like if I use 12.5 plus 12.5, that's 25. What would happen? I would get over here exactly 100 over here. But if I use 25, that means 25, 50, 75, 100. I'm using only half the scale, but it has to be more than that. So it has to be between these two. So let's say if I used 15, all right? So if I did this 15, 30, 45, 60, 75, 90, 105, and 120. And that means I get 100 somewhere over here. All right, that's a good scale as well. All right, or I could have used 20. If I use 20, 20, 40, 60, 80, 100, I'm still using more than half the scale. That would do as well. So you could also use 20, you could use 40, 60, 80, and 100. But this is a smaller scale. This is much more preferable. But this is going to be easier to read. That's going to be more complicated. So that's one of the ways of choosing your scales, right? Let's look what we're going to do. We're going to now plot these over here. Let me just do that for you. Okay, so be careful in selecting that. So I'm going to be choosing this scale, and let's see how it goes. Now, we realize if you look at this on the y-axis, we're supposed to get on the y-axis, we're supposed to get like 5.71 to 3.12, or let's go from 0 to 5.71, and which we easily do. And individually, each scale over here, this is going to read, if this is 0.5, 0.5 divided by 10 is 0.05. That means this two of these small squares is 1. So 0.1, 0.2, and 0.3, 0.4, 0.5. That makes it easier to read once you've done that. And if we choose this scale, the latter one, not this one, this is going to be very, very complicated. But this makes it easier. It's not very accurate, but it's more than half the scale, so it fits the bill, and we could use that. And besides, the second thing is it's got nice whole numbers. Look at this. Got 20, 20, 40, 60, 80, 100. Perfect. So there's not going to be too much struggle. So at 20, we have got 3.12. This is 23.1 and just about there. So half a square is just what, 40. We need 3.5, 6, 7, just a little above that. 60 is 4.34. So that's 4.1, 2, 3. That's 3, and just a little above that, just a little. All right, and 80 is 5, a nice whole number both ways, right in the middle of there. And 100 is 5.71, 5.5, 6, 7, just a tiny above that. Now, let's see if that's a nice straight line. So I get, if I join this, I get, there you are. So there you are. Fits perfectly, right? And now we have to find the gradient. In order to find the gradient, what you're going to do is that you're going to choose any number. We're going to choose this part, okay, which is 20 and 3.0, and but that's a slight error over there. And we're going to choose this because this is the way we get a nice straight line. And then I'm going to choose one of these numbers, let's say over here. It doesn't have to be 50 over 5 would be great, but you have to choose something beyond that. So let's choose this one, which is over here. Okay, so, and then you're going to draw, make sure you indicate what are the numbers you're using, because they don't have to be from the table. And then you show these markings on the graph. Okay, and use a sharp pencil. Get yourself a mechanical pencil to do that. What was our other number? It has to be more than half. So let's choose 75 is also chosen. No, 75 isn't. So 75 is a good number. Hold on. Oh, that's 100. So 60, 70. Yeah. 60. No, that's 80 and that's 100. That's 90. So you just choose 90. And that's the hair. So we're choosing this, which is right in between. Yeah. So there you are. So once you mark that, mark these 2 points to find your gradient. This is going to be 5.0, 5.1, 5.1, 5.2, 5.3, 5.35 minus our other is 3.0, and we get 90 minus 15. Sorry, that's 20. That's 20. Misreading that. That's 20 over here. Okay. Oh, sorry. I didn't realize I wasn't off the camera. So we just took these values, which is 5.35 and minus 3.0 over the corresponding value over here, which is 90 minus 20. Let's see what we get for that, the gradient. So this gives us 0.003357. Now this, we could round it like 0.0033, but since this is bigger than 5, so this will go, we'll get 0.0034, and the y-intercept over here is 2.1, 2, 3, about 2.35. 2.35, yeah, 2.35. Theory suggests that this is the value of RW. All right, so come on, this is an easy mark. So even if you've got wrong values over here, just put the values here right, and it'll become an error carried forward. But don't mess up with this part, because all you have to do is take these values, whatever values you get over here, you put them over here. So this becomes like our RW is going to be like RW is equal to 1000 multiplied by 0.0034 divided by the value of C, which is 2.35. So we get multiplied by 1000, which is this, divided by 2.35, which gives me 14.28. So 14 point, that's the ohms we're going to get. So we're done with this part of the question. I think this would be it, or is there something more? Yeah, we get to question number 3 now. So all we have to do is follow the instructions and everything's going to be fine, okay? Our student investigates the indentations made by a glass ball in the surface of the modeling clay. Describe briefly how to use the apparatus to determine the diameter of the glass ball. So now think about this. A student investigates indentations made by a glass ball in the surface of modeling clay. Now, if we had modeling clay, we can't measure really the depth. That's going to be complicated. But if we could measure the diameter, okay, let's see how it goes. Describe briefly how to use, but I think the best thing to do is to read the entire question before we set off answering it, and because otherwise you might get wrong ideas, and then you might answer according to your understanding, which might be wrong. Describe briefly how to use this apparatus to determine the diameter of the glass ball. Draw a label diagram of the arranged apparatus to help your explanations. Okay, I'm going to read the entire question. I suggest, obviously, the reason is I want you to do that. The student uses the glass ball to make an indentation in a piece of modeling clay. Shows the product that is being used. Okay, and okay, a 300-gram mass with weight F1 is placed on a wooden strip directly above the glass ball. The mass is left in place for 1 minute and then removed. Okay, so this is how it's going. Now let's do this part ourselves. Now draw a label diagram of the press to help you with your explanations. We're going to place the ruler over here. Mind you, what do we have to do over here? Describe briefly how to use the apparatus to determine. This is what we have to do. We have to determine the diameter of the glass ball. That's our task. So something we've done a lot of times is to use set squares like this and place the glass ball and subtract the reading. But unfortunately, we've not been given 2 set squares. So this is not going to work. I'm just trying to give you an idea that we actually had to do L1, L2, and the diameter would be the difference between these two. But since we're not given the second set square over here, what you would going to do is that you're going to place the ball over here, and you're going to place the disc over here and a disc over here, and you're going to use the set square to align with the edges of the disc. Okay, so this is the disc. Obviously, the discs, like if this was a ruler, you place the ball over here and the discs come like that. And then we use the set square to mark this, let's say L1, and this with the set square as well when it's going to be placed over here as L2, and that will give us the diameter of the ball. Okay, that's the diagram, not this one, but this, given the situation. And we've been given the adhesive putty to make sure that it sticks and doesn't move. So we could use the putty to stick these things to the ruler, and so they don't move. Yes. Now, the student uses the glass ball to make an indentation in a piece of modeling clay. Shows the product used. A 300-gram mass with weight F1, 3 newtons, is placed on the wooden. So this is directly above that. The glass ball. The mass is left in place for 1 minute, 1 entire minute, and then removed. Okay. Excuse my flu. The student repeats the experiment with the ball on the different parts of the clay and the 300-gram mass hanging at the end of the wooden strip as shown in figure 3.3. The lengths X and Y in figure are both shown to scale of 1 to 5. The actual lengths X and Y are 5. He's saying it two times in 2 different ways. That this length is actually 5 times more. So he's saying it in 2 different ways. Measure X and Y. So measure it as carefully as you can. We have to measure from this dotted line to that dotted line. And this is 3.5, 3.6. Make sure you're making no errors. That's 3.6. X is 3.6 centimeters. So that's 36 millimeters. Okay, because we understand that 1 centimeter is equals to 10 millimeters. So this is 3.6 millimeters. That's 3.6 multiplied by 10. And this is 7.1, 7.2. So 7.2 times 10 is 72. So this is 72. Now this is going to be 36 times 5, and okay, and this is going to be 72 times 5, which is equal to 36 times 5, 180, and 72 times 5 is 360. All right, the actual length is so many millimeters, right? So we understand that 1000 millimeters equals to 1 meter. So this is going to be 0.18 meters, and this is going to be 0.36. Am I in the frame? I'm sorry, I wasn't in the frame. 0.36 meters. So calculate the force F2 on the clay ball using the equation. Now, I'm not sure when we print this paper, right? It's not exactly to scale. So yeah, this on the mark scheme, this is not within the limit. It's less than the limit, but I tested it again and again. Turns out that the image has been shrunk. So when we photocopied this was a shrunk image. slightly smaller. So in the real paper, it's going to be, but obviously the paper you get, you're supposed to be measuring the what's on the paper, which is going to be right and accurate. So if you compare these values in the marks, according to the mark scheme, you'd find some slight errors there in my calculation. It's not going to be in accordance with the mark scheme because I'm measuring the actual value over here. So maybe this was going to be 3.7 and this is going to be 7.3 or 7.4 in the actual marks paper. So since this is a photocopy, it might have a slight variation there. So that's a caveat, but this is how you're going to do it, right? So all you have to do is like, I mean, you realize in this paper, you're just like measuring lengths with a ruler, putting that down, converting millimeters to meters, just being careful about that. This is how simple the ATP paper is. Just that, be wary. Now you're just going to take these values and put them over here to find F2. What are you going to do? 3 times Y, which means 3 times this, which means 3 times 0.36. If you're going to mess this up and lose those marks, that's going to be a shame. How difficult is this? Yeah, 3 times 0.36 is 1.08 divided by 0.18, which gives you 1.08 divided by 0.18, which gives us a whole 6.0 newtons. Okay, this is the value we get from our calculation. Let's see what else we have to do. Now here's how I did this. I mean, you realize that when I made that a certain scale, this is an A4 paper. So A4, hold on, this is not really moving very well. So I actually did this A4 with A4. It's exactly, actually, okay. Whoa, come on, focus. I don't know, it's getting an error over here. So here you go. I'm going to try again, set it again to the real length. This is an A4 paper, real paper. Okay, it's exactly the same length. All right, here you are. Exactly the same length. Once I get that, then I get the actual values over here. Look at that. And on the screen, this gives me 4. X is a nice crisp 4. All right, exactly 4. All right, I don't know why my camera is showing otherwise. I mean, like I see it, and the other one's 8. Exactly 8. And that's why we were getting an error in our reading over here on the paper, because it was slightly off in this value, X and Y, which is actually 3 so it's shrunk quite a bit actually, the photocopies. So that's why I was getting that error. The actual values are a little bigger on the real paper. Okay, so when the ball presses into the surface of the clay, it makes a small circular mark. This mark is called indentation. Shows the indentation made by the glass ball in the surface of the clay. The indentations are drawn full size. The smaller indentation is made by a mass position on, as shown in figure 3.2. The large indentation made by mass position as shown in figure 3.3. So this is what happens. All right, this is the smaller indentation with a lesser mass, and then when you add more mass on this side, it creates a greater force, a moment as well, which pushes the ball down further into the, and then obviously this is a larger indentation. Now what we have to do is draw the diameter D1 and D2. All right, so this turns out the diameter over here, very carefully, if I look at this, is 0.3. So I'm just going to use whatever is written over here. 0.3 centimeters. Sorry, this is 0.3 centimeters. So this would be multiply that, which is 3 millimeters. Okay, so, and this is 0.5, 0.6, 0.7, it's 0.8. So this is 8 millimeters. Okay, so that's how this is. Now, diameter of the larger indentation D2. What was this? 0.4 millimeters. This is 0.4, sorry. 0.4. This is 4 millimeters, and that's 8 millimeters. Be sure. Let me be sure. Yeah, that's 8. So the actual might be a little bigger. So this might be 0.5 and this might be 0.9 or something like that. The graph shows the relationship between the diameter of the indentations and the surface of the modeling clay inside the indentation for the glass ball. So here we are. Okay, this is the surface of indentations, and that's the diameter of the, what do we have to do? On figure 3.1, plot the data shown in table 3.1. Sorry, here it is. Sorry, keep going out of the frame. Diameter of the indentation, 10, 12. Now, the problem was we're drawing with the graph. Otherwise, I could have used more advanced technology and done it on my computer and annotate the soft copies. But drawing the graph is a little difficult on that. That's why I went old school and did it actually on paper. But anyway, so we have to, 10 millimeters is 90. All right, 10 millimeters is 90. So if this is 80, that's 90. That's going to be right in the middle over here. That's over there. Okay, right there. And the other one is 12 is 141.3. 12 is 141. That's 142. 140. No, that's 20 divided by 5. 20 divided by 5 is 4. So that's actually, this is 144. So this is 141, would be just actually close to that value. Just slightly, like extremely a fraction. All right, that's how it is. So on draw the best fit curve. All right, that's going to be, so if I were to draw this, it's going to turn out to be, now because I want this to be on either sides, so it's not going to be, that's the way it's going to be. Okay, so this is how it's going to be. Try that this hairlines don't appear. This is an error. This should not happen. All right, use figure 4.5 to determine the surface area A1 and A2 of the modeling clay inside the indentations where diameter D1 and D2 recorded in C. Show your graph how you arrive at your answer. Okay, that's a good one. So mind you, let's have a look at this question. I want to be in the frame. Use figure 3.5 to determine the surface area A1 and A2 of the modeling clay inside the indentations where the diameters D1 and D2 recorded in C. Show on your graph how you arrive at your answers. So we want to find the areas of A1 when the diameter was D1 and the area of A2 when the diameter was D2. So in order to do that, these are your D1 and D2. These are the values that we have. All right. And let's say how we use this graph to find those values. What you're going to do is that 4 millimeters, this is 4 millimeters, and find its corresponding value. So over here, I'm going to mark this on the graph with a dot line. There you go. And with a dot line here, which goes slightly like that. Okay. And then the other one's 8 millimeters. So that'll be this. And this is going to be over here right in the middle. So for D1, I'm getting this. Since each one of this, 20 divided by 1, 2, 3, 4, 5. 20 divided by 5 is 4. So that means this is 4, 8, 12. And this is 14. Yeah, 14. Yeah. So here you have it. So we put that 14 over here, millimeters square, and for 8 we get 44, 48, 48 plus 4, 41. 4 times 3 is 12. Okay, so 40 plus 12, 41 to 48, 52, and that's 56, but that's between 56, 52 and 56. So that's a good round number, 52, 54. So it's 54. All right, there you have it. So we're done with this part, and that's how you had to do it. All you had to do was follow the instructions and be very careful when you were. Another student claims that A2 is equals to KA1 and F2 is equals to KF1, where K is a constant, F1 is equals to 3 newtons, and F2 is your answer to B3. Using your values. Now, so these are, where K is a constant, obviously we can see that K's are constant, but there are two values for constant. So let's take the first value of F from F. So our value for K is equals to F2 over F1. K is equals to F2 over F1. Now, F2 is your answer to B3. Here's our answer to B3, and that's 6 newtons. So we've got 6 newtons F2, right? And this is given 3 newtons F1, that is 2.0. So it's 2.0. Now let's take another value of K, which is A2 over A1. And this is from this plate. We just did that right over here. That's our A1 and A2. That's 54 and 14. All right, so here we have 54 over 14, which gives us 54 divided by 14 is 3.857. So let's say 3.86. Yeah. So we realize this 3.86. Now these values are way beyond. They're absolutely no. They're too far apart. They are not within 10% of each other. So these the claim is incorrect. These two values are not within the 10% limit. So no, it's too far apart. So a student in another laboratory obtains different values of A1 and A2 using the same arrangement of the apparatus. Identify two variables that should be controlled to ensure similar values of A1 and A2 when using modeling clay. So the other control variables that you have to keep constant is that the modeling clay doesn't dry out, so it has the same consistency. The hardness of the clay. I wonder if the temperature of the clay is going to affect it. The viscosity of the clay, making it more malleable. The time for which the force is being applied, like for how long, because it keeps sinking in if the force was applied for a long time. So the size of the ball, the mass of the ball does not change. So those are the variables that you're going to have in the control. I hope that helps answer this question. Now let's go to the last question, last bit. Now, generally, this is one of the questions that students mess up a lot. It's got usually 6 marks. Let's see how, yeah, it's got 6 marks, okay, overall. Now, this question is actually very simple. If you just read the instructions and do exactly as you're told, just keeping in mind some of the factors that are listed over here in bullet points, make sure they're all covered. Like, for instance, let's think about it. A student investigates the factors affecting the bend angle theta of the metal strip, this angle. Obviously, if you put more weight over here, there are two ways in which we can cause this to bend more. Either if the weight was the same, if we move this apart, it will bend more. That means if these stands or the supports were moved further apart, between this distance is also given. Increasing the distance, all right, or decreasing the distance would cause the change in bend, or we could, if the distance was kept constant, changing the weight. Let's see how things go. A student places a thin straight metal strip on 2 supports and attaches a mass of weight W to the middle of the strip. The metal strip bends as shown in figure 4.1. Plan an experiment to investigate one of the variables affecting theta. So let's say we're going to keep the weight constant and going to just move the stand back and forth and changing D. So we'll study how D varies theta. All right, or theta varies with d, because d is going to be the independent factor and theta is going to be the dependent factor. In your plan, you should explain briefly how to carry out the investigation, including how you measure theta. Now, we use a protractor, of course, to measure theta. So you must mention that we are going to use a protractor to measure theta. We're going to clamp it close to it so that we can measure the values. So avoid the parallax error, and state the variables to control the thickness of the metal strip, making sure the metal strip is of the same type. And then we are going to make sure that if we are looking at, since the weight is going to be kept constant, if d is the variable with theta, or if you're saying d is kept constant if weight is the variable with theta. All right, and draw a table or table values. Now, so if you were drawing this, you would say d in centimeters and theta in degrees. Okay, so you do not forget to write the units. Or you could say, with if mass was constant, so if mass in grams and theta in degrees, and with in this situation, if you were drawing this table, then you're going to keep the distance constant. Okay, we don't have to enter the value, but you do have to show that 1 2 3 1 2 3 over here 1 2 3, that we're going to take about 3 values. Explain how you would use your readings to reach a conclusion. We would compare by drawing a graph and looking at the gradient of the graph to look at the trend. All right, so one would be naming the instruments that are over here. What are the variables that you are going to compare? Like we are going to say we are going to vary d with everything else constant, which is the mass constant, the steel rod constant, the material of the steel rod is the same. At the temperature is not really affect. It could affect. I mean, it gets temperature, but not that much. But anyway, what are you going to keep constant? You're going to have at least more than 3-4 values that you're going to take between different lengths of d and theta recorded. All right, make sure the units are right. Okay, and then we're going to compare by drawing a graph of d with theta. D going to be on the x-axis and theta going to be on the y-axis, because it's going to be a variable. And then you say, do not make a conclusion because you've not conducted the experiment. Then that's how you're going to say. So these are the 6 marks you're going to get. This is not going to be a problem if you make sure these points are there. Okay. Let me know if this is helpful. Let me then make another one. Obviously this was an effort in an analog form, and it's pretty bad in terms of taking a lot of time. I try to do it faster. Let me know if you want me to make another one.